Hello and welcome to Problem Set 15. Our problems today are from the topic An Introduction to Nuclear Chemistry. Before we get started with that, just a quick reminder that the worksheet that I will cover today is available online through my website. And with that said, let's go ahead and get started with number one. Number one, how many protons and neutrons are in the following isotopes? And there's an A through D. A is sulfur 35. Okay, so I'm going to go ahead and convert this into a proper symbol. Sulfur and the particular isotope of sulfur, sulfur 35. Remember that 35 is going to be the mass number for the isotope, which is always written as a superscript before the element symbol. Now all we're missing here is the atomic number, which we will have to get from our periodic table. So grab your periodic table and look up sulfur. It is in group 6A and it has an atomic number of 16. All right, so the number of protons always given by the atomic number. You just get that straight from the periodic table. But the number of neutrons can vary depending on the isotope of the element. So this is sulfur 35. So we're going to find the number of neutrons by using both of these numbers. We know that the mass number is the sum of the protons and the neutrons. So the sum of the protons and the neutrons is equal to 35, and we know that the number of protons is 16. So we're going to plug that in, plus n equals 35. So we're going to solve for n by subtracting the 16 from the 35, and we will find that this particular isotope of sulfur has 19 neutrons. So I'm going to write it up here. I'll circle my final answer there. Okay. B, neon 24. All right, so I'm going to do it the same way. I'm going to go ahead and convert this to a proper symbol with the mass number and the atomic number. So the mass number is 24. That's got to be given for the particular isotope in question. The atomic number you're always going to get from the periodic table. So neon is a noble gas, so find it in group 8A. Its atomic number is 10. So we know the number of protons is 10. The number of neutrons can be found from subtracting the number of protons from the mass number, leaving you just with the number of neutrons. So that would be 14 neutrons. C, indium-113. All right, so again, I'm going to write the mass number as a superscript before the element symbol, and I'm going to go to my periodic table and find the atomic number for this element. Indium is in group 3A, if you're having trouble finding it there, look in group 3A, and it has an atomic number of 49. Okay. So the number of protons must be 49. The number of neutrons we would find from subtracting 49 from that 113. Okay, so what's that going to be? 64. Okay, and D. Last but not least for number one, boron 10. Okay, so again, I'm going to go ahead and put the mass number as a superscript before the element symbol, and then I'm going to go to the periodic table. Boron is also in group 3A with an atomic number of 5. So number of protons is 5. Number of neutrons then must also be 5 for that isotope of boron. Okay, so that is all of number one. Let's go ahead and erase here and go on to number two. Okay, number 2. How does the mass number and the atomic number of a radioisotope change when it undergoes alpha decay? So I'm going to write here alpha decay. So remember that in alpha decay, 2 protons and 2 neutrons are ejected from the nucleus as an alpha particle. And so that's going to affect the atomic number because the loss of the 2 protons is going to drop the atomic number by 2. So I'm going to write decreases by 2. It's going to affect the mass number because remember the mass number is the sum of the protons and the neutrons. So if you lose 2 protons and 2 neutrons, it's going to drop the mass number by 4. So I'm going to write here decreases by 4. Okay, so how does it affect the atomic number and the mass number? The atomic number will decrease by 2 and the mass number will be decreased by 4. So you can always figure out what element, what isotope of what element is going to form from an alpha decay by going to the periodic table and looking up that new atomic number and then calculating that new mass number. All right, number 3. How does the mass number and atomic number of a radioisotope change when it undergoes beta decay with the release of gamma radiation? So I'm going to write up here beta decay with gamma radiation. So remember that in beta decay, a neutron decomposes into a proton and a beta particle, an electron, which is ejected out of the nucleus. So how is that going to affect the atomic number of the element undergoing that decay? Well, the atomic number, remember, gives you the number of protons. A neutron decomposes into a proton and a beta particle. So the atomic number is going to increase by 1. So I'll write here increases 1. The mass number, being that the mass number is the sum of the protons and the neutrons, well, you're losing a neutron. A neutron is decomposing and turning into a proton and a beta particle. So down 1, up 1, it cancels out. There's no change to the mass number in a beta decay. Okay, so no change. And I threw the gamma radiation in there just to kind of make it tricky. Remember that gamma radiation is just a form of high energy electromagnetic radiation. It is massless, and so it doesn't actually affect your number of your atomic number or your mass number. Okay, so the answer to number 3 is that you would expect the atomic number to increase by 1 and you would expect no other change. Okay, number 4. What isotope results from alpha decay of astatine 2O4? So let's go ahead and just write the alpha decay reaction here. And so we're going to need to write a proper symbol here for astatine 2O4, and for that we need to know the atomic number. So I'm going to go back to my periodic table. Astatine is a halogen. The atomic number is 85. It's given in the problem that this is going to undergo alpha decay. So the first thing I like to write as my product is the alpha particle that is going to form. Remember that it's a helium particle, 2 protons and 2 neutrons, so a 2 and a 4 here. Now, what is the new element formed? Well, the new element formed is going to have an atomic number that has decreased by 2 because of the loss of those 2 protons in that alpha particle. So the new atomic number is 83. The new mass number for that new element formed is going to be 200. It lost 2 protons and 2 neutrons, so the mass number decreases by 4. So let's go to our periodic table and figure out what element has the atomic number 83, because there's only one element that has atomic number 83. So let's see here. Okay, so we're in group 5A, bismuth. So I'm going to write Bi, not just any bismuth, but bismuth 200, this particular isotope of bismuth. So what is the isotope that results? This is the isotope. Bismuth 200. Okay, number 5, I think we can squeak it in here before we erase. What isotope results from the beta decay of strontium 90? So again, I'm going to go ahead and just write the whole nuclear reaction. It's really easier to do it that way. I'm going to need the atomic number of strontium. It's in group 2A. Its atomic number is 38. We know that it's beta decay, so I'm going to go ahead and just write as my first product the beta particle. Don't forget how to write that. It is an electron, so we write the -1 to help us remember that the atomic number is going to increase by 1, and we write the 0 to remind us that the mass number is not going to change because a neutron decomposed into a proton and this beta particle. All right, so the new element formed will have the atomic number 39 and the mass number 90. So go to your periodic table and find atomic number 39. It is yttrium. Okay, so this is the isotope that will form from the beta decay of strontium 90. It's yttrium 90. Okay, let's go ahead and erase here before we go on to number 6. Okay, number 6. Carbon-14 is used for radioactive carbon dating and can date artifacts between about 1,000 and 20,000 years old. Carbon-14 undergoes beta decay. Write an equation to show the decay of carbon-14. Okay, so first thing we need to do is write the appropriate symbol for carbon-14. So find carbon and find its atomic number. Its atomic number is 6. The 14 is written as a superscript, that is the mass number, and it is given in the problem. And it's undergoing beta decay, that's also given in the problem. So go ahead and write in as your first product that beta particle, which is written always like this. So the new element formed is going to have an atomic number of 7. Remember that beta decay is when a neutron decomposes into a proton and a beta particle. So the atomic number is going to increase for the addition of that proton. And because we lost 1 neutron but we gained 1 proton, the mass number is not going to change. So go to your periodic table, find the element that has the atomic number 7. It is nitrogen. So nitrogen is a new element that forms from the beta decay of carbon-14. All right, let's go on to number 7. Cobalt-60 is useful in radiation therapy and food irradiation. It undergoes beta decay accompanied by the emission of gamma radiation. Write an equation to show the decay of cobalt-60. So cobalt-60. All right, so remember that the 60 is the superscript for the element symbol. Go to your periodic table, find cobalt. Its atomic number is 27. It's given in the problem that it undergoes beta decay, so go ahead and write your beta particle first as your first product, and then figure out all the details for that new element that's going to form. It's going to have an atomic number 1 greater, so 28, but the mass number will not change. Now go to the periodic table and find out what element has the atomic number 28. It is nickel. And then in the problem, it says that this is accompanied by the emission of gamma radiation. I always like to show the gamma radiation with the symbol 0, 0. So gamma with a 0 and a 0. Some textbooks will tell you to leave that off because it doesn't actually affect the identity of the element formed, but I like to show it because that shows that there is this high energy electromagnetic radiation being given off during this reaction, during this nuclear reaction. All right, number 8. Let's go ahead and erase for number 8 because it's got an A through C. We might need a little extra room. Number 8. Uranium-238 undergoes a series of nuclear decay reactions, both alpha and beta decay, and ultimately ends up as the stable isotope lead-206. One of the intermediate decay products is radon-222. Radon gas is readily inhaled and exhaled, but if radon undergoes alpha decay while in the lungs, it will release ionizing radiation to the delicate tissue. Given this information, complete A through C below. A, write a nuclear reaction to show the alpha decay of radon-222. Okay, so we need to go to the periodic table, find radon. It is a noble gas with atomic number 86. We know from the problem that it undergoes alpha decay, so go ahead and write the alpha particle as your first product. And now we need to figure out what is the new element that will form. So it's going to lose 2 protons. The new element will have atomic number 84, and the particular isotope of that element will have a mass number of 222 minus 4, so 218. So go to your periodic table and find out what element has atomic number 84. It is polonium. Okay. So there is our alpha decay reaction for radon-222. B. Would you expect the product of this decay to be stable or unstable? Why? So hopefully you take a look at this atomic number and you know instantly that this must be unstable. It must be radioactive because all isotopes of all the elements with an atomic number greater than 83 are radioactive. Remember that band of stability that we looked at in tutorial number 15. It halts at atomic number 83. There are no stable isotopes beyond atomic number 83. So we're going to write for B that polonium-218 must be radioactive or unstable because all isotopes of elements with atomic number numbers greater than 83 are unstable. They are radioactive. So I'm going to write here in parentheses, they are beyond the band of stability. Okay, and C, last but not least, the product of this decay is a solid. So polonium-218 is a solid, which becomes trapped in the lungs and causes further damage. If this product is radioactive, what type of decay do you expect it to undergo? So again, going back to tutorial number 15, we said that usually atoms or isotopes that lie beyond the band of stability, that have an atomic number greater than 83, usually they will undergo alpha decay, losing 2 protons and 2 neutrons in the form of an alpha particle. So we would expect polonium-218 with an atomic number of 84 to most likely be an alpha emitter. So I'm going to write down here, most likely an alpha emitter will most likely undergo alpha decay. Okay, so this will conclude our problem set 15. I hope you will consider tuning in to tutorial number 16, where we will jump into an introduction to organic chemistry. Thank you very much.